Please welcome Laser Science General Chair Elaine Lee and Co-Chair Hailin Wang.
Hello and good morning. Welcome to the second plenary session of the Frontiers in Optics and Laser Science. This week, we have all benefited from the high-quality technical sessions, panel discussions, and poster presentations, and exciting technology demonstrations, exhibitors, and show floor program in a science and industry showcase.
It's exciting to see such a high level of engagement from our attendees, speakers, presenters, and exhibitors. We are truly grateful to our speakers and presenters for their insightful presentation on topics ranging from quantum science and technology, nanophotonics, ultrafast dynamics, to strong field physics. The technical content of this conference is the result of dedication and hard work of dedicated group volunteers.
Hailin and I have the privilege to building this exciting conference alongside our outstanding program chairs and committee members. Let's recognize their effort with a round of applause.
We're excited to unite the APS and optical communities under the common goal of exploring the latest research and applications in our fields. This conference will foster new connections, help us to reconnect with old friends, and most importantly, nurture the next generation of scientific innovators.
I'm honored to serve as the past chair of the APS-DLS and to be here on behalf of our members. This year, we're embarking on a special milestone as we celebrate 40 years of advancing our mission to promote laser science interests within the APS and represent those interests with other societies, such as Optica. Each year, we convene as a committee here at FIOLS in concert with Optica to reflect on the year's development and look forward to what's next.
For over 2 decades, the APS-DOS Symposium on Undergraduate Research has been a part of our annual meeting and a satellite to this conference. The symposium provides students with the opportunity to present what are often their first research papers to a global and esteemed audience. Our division also sponsors a number of awards for both early career professionals and established scientists. This includes the Carl E. Anderson Dissertation Award that recognizes doctoral research in laser science. In a special session earlier this week, a panel of judges heard talks from 4 extremely talented finalists: Emily Caldwell, University of Colorado, Boulder, and NIST.
That's how it is.
Dhruva Galapathi, Massachusetts Institute of Technology. Badr Elias, Massachusetts Institute of Technology. Haiwen Wang, Stanford University. We are pleased to congratulate the recipient of this prestigious award.
So we also sponsored Arthur Shallow Prize in Laser Science, which recognized outstanding contributions to basic research using lasers to advance our knowledge of fundamental physical properties of materials and their interaction with light. This year's recipient, Vladan Volatic, is recognized for his pioneering work on spin squeezing for optical atomic clocks, quantum nonlinear optics, and laser cooling to quantum degeneracy. Hailin and I are also thrilled to note that Vladan happened to be the laser science plenary speaker this year. Vladan is the Lester Wolf Professor of Physics at MIT. As a student, he first learned about a scientist who had managed to cool atoms using a laser to minus 273 degrees Celsius, which is close to absolute zero. Although he wasn't sure of its practical application at the time, he was fascinated by this discovery and decided to pursue the field of cold atoms or quantum physics. Throughout his career at Stanford at MIT, Vladan has led many groundbreaking experiments, including the accidental creation of a lightsaber, a fictional energy weapon from the Star Wars universe. In 2013, not a long time ago, and not in a galaxy far, far away, Vladan and Harvard physics professor Michal Lukin conducted an experiment that involved firing photons through a cloud of matter cooled to a temperature near absolute zero. This experiment demonstrated that mass-like interaction between photons are possible, suggesting that lightsaber, the colliding beams of light, wielded by the Jedi and the Sith in the Star Wars franchise, may one day become a reality beyond the realm of science fiction. His current research interests include ultra-cold atoms, laser cooling, many-body entanglement, and quantum physics. Vladan has authored over 150 articles in the fields of atomic physics, laser cooling and trapping, precision measurement, and quantum physics. He is a fellow of APS, an American Association for the Advancement of Science. Please join me in welcoming to the stage Vladan Volatic.
Okay, good morning, everybody. It's a special privilege and honor to be here. And I would like to tell you a few applications of atom-light interactions. I will not be covering lightsabers today, partly because I don't want to deal with a barrage of emails of enthusiasts, as happened last time. I will tell you about two topics. One of them is atomic clocks and spin squeezing, particularly how to use entanglement to make it a useful tool to overcome certain limits, like the standard quantum limits. And then something which goes beyond the work of the award, which is neutral atom quantum computing with Rydberg atoms. My talk will, motivate why light atom interactions are a quantum tool with neutral atoms particularly that are very clean quantum systems. I will then tell you a little bit about metrology with entangled atomic states, the so-called standard, I will remind you or tell you what the so-called standard quantum limit is for atomic clocks and atom interferometers, for independent particles, how entanglement, or in particular so-called spin squeezing, can overcome this limit on the example of optical transition, which are the most advanced atomic clocks. And I will also tell you a little bit about how switching the sign of a many-body Hamiltonian, which according to quantum mechanics leads effectively is equivalent to an evolution backwards in time, leads to new possibilities for quantum metrology. And then in the second part of my talk, I want to tell you a little bit about manipulating atoms with lasers for quantum computing in so-called atomic arrays and quantum error correction logical qubits that have become very recently available in these systems. So light atom interactions, they are strong interaction. Light atom interactions are an excellent quantum tool because we can control all quantum aspects. In particular, interest in my work is my own work and that of others is the interaction of a single atom with a single photon. It turns out that you can bring this into the quantum realm in the regime of so-called cavity quantum electrodynamics, or cavity QED. There are a few ways to use these. One can use photons as quantum messengers between the atoms to produce effective long-range or infinite-range atomic spin-spin interactions that I will tell you about, which can then create entangled states of hundreds, thousands, or tens of thousands of atoms, up to millions. And I will tell you how to apply them for quantum measurements. And then other approaches are, light to precisely control atomic states, like qubit rotations, 2-qubit gates that we do by laser excitation, etc., for quantum computing. So just to set the stage, what is cavity quantum electrodynamics? The goal is to couple a single atom strongly to a single photon. And one simple way to think about this is to say, well, I'm going to focus the beam as tightly as I can to some beam area A. I'm going to place an atom in the middle of the beam. The atom has a cross-section, which is sigma, which is on the order a little bit smaller than the wavelength squared of the atom. So even though the atom is fairly large, the diffraction limit prohibits us from focusing the laser beam down strongly enough so that we get strong interactions in free space. However, we can get close enough with a small beam so that when we add mirrors to the system and let the photon pass through the atom many times, and you can do this, say, up to 100 or a few 100,000 times with the best mirror coatings, then you can basically multiply this ratio of cross-sections with the number of passages, and this number is a dimensionless number that we call cooperativity. And if you meet the criterion that this product of the ratio of the cross-sections times the number of passes is larger than 1, the cooperativity is larger than 1, then you're working in a strong coupling regime where actually the coherent exchange between the atomic excitation and one photon in the cavity is faster than any decay processes like losses in the mirrors or the atom emitting light into free space. And that is the regime of strong coupling cavity QED. You can quantify this. Basically, this is more formally the cooperativity parameter, which goes as the finesse of the cavity. Finesse over pi is the number of round trips. And then this denominator here is the ratio of the atomic cross-section squared divided by the beam weight squared. So this is to take away one needs strong coupling. If you have this strong coupling, then if I plot on a frequency axis, say the transmission through the cavity, and I place an atom inside the cavity, then what happens is the cavity mode splits. And you get the famous so-called vacuum Rabi splitting. Basically, you get a hybridized mode between the atomic excitation and the cavity excitation as a signature telltale of strong coupling being achieved. And it can be used, for instance, for quantum networks, quantum repeaters, and I will tell you here about approaches to use this to entangle many atoms. So let me tell you about so-called spin squeezing and improved measurements. The best atomic systems or measure quantum sensors are those that measure a phase evolution difference between two states. So you identify and isolate two states, say in an atom or in any other stable system. You prepare quantum superposition between these two states. We know that according to the rules of quantum mechanics, the phase difference between these two states evolves at a frequency proportional to the energy difference between the two states. And then if you want to measure a parameter, you make it such that the energy depends on that parameter, say magnetic field, electric field, etc. Or for a clock, you try to make the energy not depend on any parameter as far as you can control it and use it just to quantify time instead. And then finally, to measure the phase, we perform another rotation on this spin or qubit quantum system to convert the phase into a population difference between those two states that we can read out via measuring the upper and lower state. Now what happens is we would like to make the measurement precise, so we are going to use not one atom, but a collection n of atoms. We try to make n large, and then the measurement with n atoms improves the signal-to-noise ratio as square root of n. And the reason is very simple. You have n atoms, so you have n times the signal, but we know that the projection noise, or shot noise if you want, scales as the fractional noise scale as 1 over the square root of the particle number. This is simply because in the end we are measuring one of two quantum states of the atom, and so that's like flipping a coin, and if you flip 100 coins on average you expect 50, but on any individual run you see deviations from that by a binomial distribution that can be approximated as square root of n in the limit of the large quantum number. So this is the so-called standard quantum limit. It's the limit where your precision improves with system size, particle number as 1 over square root of n. And this is the limit if you use independent particles. However, it is possible to overcome this limit by entangling the systems. Let me explain to you how that works. So first of all, if we have n particles, we think of, instead of the individual particle spin of the two-level system spin 1/2, we imagine all atoms doing the same, so we sum them up to a large spin or large angular momentum, n over 2. And then we know, according to the quantum mechanical rules, that the angular momentum direction cannot be perfectly defined. There's uncertainty rules about the angular momentum, that Heisenberg uncertainty rules that tell us that the perpendicular component of the angular momentum scales as the square root of spin. So angular momentum, you cannot perfectly point it into one direction in the quantum realm. And so how can we think about this? Think of the famous Ramsey sequence. This is the so-called Bloch sphere. This is all the atoms in the lower state, all the atoms in the upper state. This is a quantum superposition between the two states. We prepare with a so-called pi over 2 pulse, a quantum superposition between the two atomic states and all atoms simultaneously. Then we let the system evolve relative to a local oscillator, a microwave clock, or in our case, a laser optical clock. And finally, we read this accumulated phase out via another rotation about this axis, and now it shows up as a difference in population along the z-axis. And the fuzzy nature here is supposed to indicate the quantum angular momentum uncertainty rules of quantum mechanics that tell you that you can only measure with a finite precision the angle. Now, quantum mechanics says Heisenberg uncertainty relations say that the product of the uncertainty, say, along z and along y is larger than the average length of the spin vector. So, but it only constricts the area. So in principle, you can make one of these smaller at the expense of the other one being larger. So visually, if you can squeeze the noise so that you decrease, say, the noise along the phase direction and increase the noise along the other direction, the two lowest order you don't care about, then you can clearly see that I can now make better phase measurements. This goes under the name of spin squeezing, maybe more appropriately spin noise squeezing. And this requires entanglement because the atoms need to be correlated and we need to produce noise that is lower than that of individual particles. If you can make such a state, then you can really run the Ramsey sequence simply with such a state, just as before, and finally, as you do the final rotation and try to convert the phase into a population difference, you have now reduced uncertainty in the measurement. So the best atomic clocks run close to the standard quantum limit, and as I told you, the simplest form of entanglement that can overcome this limit is this spin squeezing. How can one generate the spin squeezing, in particular in a large ensemble of distant particles, hundreds, thousands, millions? If you think of the Hamiltonian, then the simplest Hamiltonian is, say, Sz. We know that that corresponds simply to a rotation about the z-axis, right? That rotates all spins about the z-axis. The next most complicated Hamiltonian you can imagine is Sc squared. You can think of this as a rotation about the z-axis by a speed or by an amount proportional to Sc itself. And so what that means is that the state above the equator rotates a little bit faster than the equator and the state below the equator a little bit slower than the equator. So overall, that shears the state and makes it into an ellipse. And Kitagawa and Ueda in the groundbreaking paper already in 1993 pointed out that this Hamiltonian generates spin squeeze states and that they are useful. It was known from the work of Dave Wineland that these are in principle useful for quantum metrology. And they called it one-axis twisting, but at the time, as they write in their paper, it was completely unknown how you would take thousands or millions of atoms and generate this collective Hamiltonian. This is not a spin of one atom, this is the sum of the spins of all the atoms about the z-axis. In the meantime, in the years that followed, people have found different ways to do it. One is you can take a Bose-Einstein condensate where all the atoms are in identical states and then use collisions between the atoms. This was pioneered by Markus Oberthaler, Mike Chapman, Yu Li, and others. However, we don't like this approach too much because that means the collisions that create the entangled states are always present and they are kind of deteriorating the performance of the clock afterwards. We would like just to make the state and then turn off the interactions. And the cavity offers effective long-range spin-spin interactions, as I will show you in a moment. In the last year or so, a new approach has also come up, pioneered by Adam Kaufman and Jun Ye, Manuel Endres, Jeff Thompson, and others, that uses Rydberg interactions that we also use for quantum computing to create complex entangled states. This approach has effective long-range interactions, so it's much easier compared to the short-range approach, so it's much easier to actually entangle large systems. So I'll tell you now how we generate this Sc squared Hamiltonian approximately. The experiments take place in an optical cavity, and we're going to use the light to generate the entanglement in the atoms. We trap the atoms inside laser beams on a so-called magical wavelength transition that traps the atoms in such a way that the atomic clock transition in the optical domain remains unperturbed. And then we apply light through the cavity, as I will show you in a moment, to create entangled states of the atoms and also to read out these states. So what do we do? This is the structure of partial level structure of ytterbium. The states that we're interested in for spin squeezing and for creating entanglements are two nuclear sublevels, -1/2 and 1/2 in the electronic ground state of ytterbium. And then we have some excited state with 4 levels. We've split these levels up with a magnetic field, and then we park the cavity on this closed transition. And what I've indicated here schematically is that when we place enough atoms in here and we're in the strong coupling regime, the cavity line hybridizes with the atomic transition and we see the split line. Or equivalent here plotted out where the horizontal axis is the frequency axis. This is the so-called vacuum Rabi splitting. Now it turns out that to generate entanglement is surprisingly easy. All that we need to do is park a laser here, a laser beam of a chosen strength, in the slope of this line. How does this work? Well, the idea is you have created a quantum superposition between these two states that has quantum fluctuations. So for the average population, say the laser has a certain detuning from the atomic resonance and there's certain power inside the cavity. That power inside the cavity acts as a light shift because we are detuned from the atomic transition and shifts the level down, say, a little bit. And then as if we have quantum fluctuations between these states, let's say that this population is a little bit smaller than on average, then the vacuum-Rabi splitting shrinks a little bit. So it's now a little bit smaller, which means our intracavity light intensity is a little bit smaller than it was before. This means that the light shift is a little bit smaller than before. And vice versa, if we happen to have a quantum fluctuation that has more atoms in this state, then the splitting is larger and the intracavity intensity sitting on the slope is larger. And therefore, the phase shift is larger. What does this do? It basically takes quantum fluctuations in the population difference between these two states, the SZ component, and converts it to an imprinted phase shift or a SY component. So it generates correlations between SC and SY spin components of the system. And this depends on the state of all the atoms because the light is seen collectively by all the atoms. So in more formal language, we have a Hamiltonian that has 3 terms. Hopefully, they're not too hard to understand. This is C dagger C is the photon number inside the cavity. So this is simply the energy of the photons inside the cavity with cavity resonance frequency omega C. The other term, the last term, is simply the atomic energy. Depending on whether the atom is up or down, it acquires, say, an optical frequency difference omega 0. And then the term of interest is a product of the photon number inside the cavity, C dagger C and SZ. And so this is you can think of this either, you can group it with one or the other of the terms. You can think of this either as changing the atoms, having a refractive index, and changing the cavity resonance frequency. And therefore, you have a different frequency inside the cavity, as shown down here. So the photons acquire a little bit different energy. Or you can think of this as the light shift, as I've described it before, exerted by the photons inside the cavity, producing a shift in the atomic resonance frequency. And formally speaking, if you take this interaction Hamiltonian, you think I'm going to linearize, say, the cavity photon number as a function of SZ, then I can Taylor expand it. There's a linear term that we can echo out, spin echo out with an appropriate pulse sequence. And so we end up with this, if you want, Kitagawa-Ueda spin squeezing Hamiltonian or one-axis twisting Hamiltonian. Now, what is interesting in this system is we would really like to generate this unitary Hamiltonian that acts only on the atoms, but we are shining light inside the cavity, and the light leaks from the cavity. It is reflected, it is transmitted, there's a phase shift on the light. So besides the process that we want, there's actually also light atom entanglement. If you carefully were to collect all the photons, you could learn something about the atomic state. Since we are not able to collect all the photons, there's losses inside the cavity. This leads to, if you want, dissipation in the pure atomic system. We are no longer in a pure state. However, if you plot as a function of frequency the strength of the interaction, so in red curve is shown the one-axis twisting strength. So basically this is near the vacuum-Rabi peak, or this is one half line away from the vacuum-Rabi peak, shown like red. And the strength of the atom light entanglement, or what we learn about the atomic state via the light, is shown by the blue curve. And so what you can see is this blue curve falls off much more quickly from resonance than the red curve. So by giving up on some of the one-axis twisting interaction strength, we can actually substantially suppress the atom light entanglement and make this process nearly unitary. That's a key component. The other thing that you need to take away from this graph is that the strength of the atom light interaction coefficient changes sign. It's a dispersive thing. So if we shine light, say, in here, we can generate a certain Hamiltonian, this SC squared Hamiltonian with a certain strength. But if we say shine light in here, we can simply switch the sign of the many-body Hamiltonian. This is a very unique feature that with such a simple switching of the laser frequency, you can actually change the sign of the many-body Hamiltonian, which will turn out to be useful later. So when we use this to make spin squeeze state, what I'm showing here on a logarithmic axis is the variance of the state measured along different angles, alpha rotation angles. Then I'm going from a round state, where the variance doesn't depend on angle, to a more and more elliptic state where I'm pushing down the uncertainty in one direction. And what you should take away from this is we are able to make spin squeeze state with about 10 dB or so squeezing, and we really run into the detection limit. We can make quantum states that are narrower and have lower noise than we can actually detect, even though our noise is only a few atoms on a system of thousands of atoms. So the real spin squeezing is actually much stronger, but we run into the detection limit. So we did first experiments on microwave clocks already more than a decade ago, together with my graduate students Monica Schleyer-Smith, who is now at Stanford, and Ian LaRue, and we demonstrated that squeezed clocks can indeed outperform normal clocks, unentangled clocks, by a few dB or so, by a factor of, say, 4 to 6. What we have done more recently is apply this to a state-of-the-art clock, not a microwave clock, or an optical clock where coherence and entangled states are much harder to maintain. So I've described to you how we spin squeeze these two states. Now I have added another level, which is the so-called clock level. And so to run a clock, you want to make a quantum superposition between these two states, but we have already spin squeezing in the ground state. So simply what we can do is we can take a so-called pi pulse and map the population between one of the nuclear ground states onto the excited state. And now we can run a Ramsey sequence, a phase evolution between these two states as we like, and then read out a signal. So the whole sequence is shown schematically up here. We start, the violet spheres indicate the Bloch spheres, or the spin 1/2 system in the ground state. The yellow sphere indicates the spin 1/2 system between one ground state and the atomic clock state that I've shown before. So the way we run the sequence is we start with all the atoms in one of the magnetic sublevels in the ground state. We do a pi/2 rotation with a radio frequency pulse to create a quantum superposition. We then apply the spin squeezing light through the cavity, create the squeeze state. And now we rotate the squeeze state such that the narrow axis, the one that has better phase resolution, is along the phase axis. Better resolution is along the phase axis. And then simply with a pi pulse, we map the system onto the clock transition in the atom. We evolve for a certain Ramsey time, tau, and then we map everything back down to read out the states. And so in that way, we can accumulate an optical phase. And it actually works. We can make spin squeeze states, shown in red here, that are a few dB better than the coherent state, the measurement with an unentangled state, like so. And as I said before, this was primarily limited by two effects. One is that actually this was done by measuring the noise in the end, and we were limited by our measurement noise rather than by the quality of the entangled state. It was also limited by the quality of the laser on the optical clock transition. So basically, you should think of the atoms as being very, very stable and rotating at optical frequencies, and then we are maintaining the phase relative to a laser at the same optical frequency for times on the order of hundreds of microseconds to milliseconds. How can we get around this limit of being measurement limited? This is an idea that Monica Schleyer-Smith and her students came up with, which is to say if we can change the sign of the many-body Hamiltonian or evolve backwards in time, then we can have the following sequence. We can start with an unentangled state and spin squeeze it. And if you imagine now displacing the state by a small amount along the narrow axis, smaller than the original size, but larger than this narrow axis now, you can see that these two states after the displacement are orthogonal to each other. They have very little overlap. Now, if we apply a unitary evolution backwards, this tells us that the states need to stay orthogonal to each other. And so that means that the small phase shift in here gets amplified and gets mapped back through the negative spin squeezing Hamiltonian onto a large phase shift. So now we no longer need to measure something narrow, like shown in the middle, but we can measure a much larger displacement. So instead of reducing the noise, if you want, we are amplifying the signal with this sequence. Something similar had been done in BEC experiments, not by switching the sign of the Hamiltonian, but by, in a free-level system, by switching atomic populations. And also in work here close to here at Boulder by John Bollinger, Anna Maria Ray and colleagues using ions and phonons in the ion crystal instead of photons. In our system, we can apply the Hamiltonian longer and longer, and you see the state that was originally a nice Gaussian gets squeezed more and more until it starts to wrap around the Bloch sphere. That's why there's more population towards the ends. But if we apply the negative Hamiltonian for each of these systems, we can almost come back to the original state with a little bit of extra width or noise. So we can both squeeze the state and unsqueeze the state. And what that means is that if we amplify the displacement, so shown here is the signal displacement that we apply, and then the resulting displacement after this whole sequence of this quantum amplification. And we see the solid line is unity curve, so that's basically what you get without entanglement. And with this spin squeezing, unsqueezing sequence, you can see that you get a much steeper line and larger signal to noise in the system. And with this system, we could now basically replace 15 measurements with a coherent unentangled state with just a single measurement with this entangled states in the sequence. So this is starting to approach interesting levels. And just to give you maybe an idea where the field is, what is plotted here on both logarithmic axes is the amount of metrological gain, where the standard quantum limit unentangled states are down here, the amount of metrological gain versus the atom number in the system. The gray area is forbidden by the Heisenberg uncertainty relations, so you can't be inside that area. But the closer you are to this area, so basically you want more metrological gain and you want more atoms, so the closer you are to this area, all the better. A few experiments with a few ions can operate near this area, but this is just a small number. The record for spin squeezing has been set by Mark Kasevich and James Thompson, both achieved to about 20 dB or a factor 100 in reduction of averaging time in their systems of large atom number. Our experiments are indicated by these red squares. So while we are not quite as high yet, hopefully, as a function of atom number, you can see that we evolve parallel to this Heisenberg limit at a fixed distance that has to do with technical limitations of our system. But basically, our improvement is not square root of n, but 1 over n, which is nicer. Maybe we have some new results on a new sequence, but maybe I'll skip this in the interest of time to tell you a little bit about quantum simulation and computation with Rydberg atoms. This has been done in close collaborations with my longtime collaborators and friends, Misha Lukin and Markus Greiner at Harvard. This is a very, very active field where lots of results are coming out almost weekly. One of the pioneers is Antoine Brouwer, but also Jeff Thompson at Princeton, Manuel Endres at Caltech, Adam Kaufman at NIST, Hannes Bernien, who moved from Chicago to Innsbruck, and also a number of companies are active in this field. Our own quantum computing company, Quera, that we founded with Misha Lukin and Markus Greiner, but also Pascal in France, Atom Computing here in Boulder, etc. Let me read you a quote from Feynman, which I find really, really remarkable. So in 1983, Feynman said the following: "Now we can," in one of his talks, "in principle make a computing device in which numbers are represented by a row of atoms with each atom in one of the either two states. That's our input. Then the Hamiltonian starts. The ones move around, the zeros move around. Finally, a particular bunch of atoms represents the answer. Nothing could be made smaller, nothing could be made more elegant." If you think that he predicted this in 1983, I think if you had read this to somebody even in 2010, they would have said, this is crazy, 50 years off, Star Wars kind of fiction. But I will show you how remarkably close we have gotten to this idea of encoding information in qubits. This builds on the work on several giants. So this was done on work on trapping, both done in Bell Labs at the time. Art Eshkin, who trapped spheres and biological samples in light traps and dipole traps, and Stephen Shu, who did the same thing for laser-cooled atomic ensemble, something that he also pioneered. So this is one of the technologies that goes into this, that is important. The other technology is to control individual atoms. Steve Chu in particular, and all groups up to the time had always trapped many, many atoms, whereas you want single atom control. So this goes back to a remarkable experiment in 2001 by Philippe Grangier's group in Paris, where basically they used technology that was already well known, a vacuum chamber, laser cooling, a so-called magneto-optical trap to laser cool atoms, an optical dipole trap, basically a laser focused into the chamber to trap atoms. The only thing that they did differently, everybody was trying to trap many atoms. They had high power lasers, large laser beams. He said, what happens if I focus the laser beam as tightly as possible? So he focused it close to the diffraction limit, a little bit less than a micrometer, and then he looked at, are any atoms trapped in the system? And what he saw was something remarkable on a camera. Here are pictures from the camera. Basically, he observed two fluorescence levels from the atoms. This lower level is simply background noise, some dark photons and so on. And then he observed remarkable stable levels that were quantized. And this fluorescence level corresponds to 1 atom. This is an axis in the second time scale. So an atom could be trapped there for second or seconds, then disappeared apparently, came back, etc. Now, it's not only remarkable that you can resolve 0 for 1 atoms in this picture. What is maybe more surprising is that you don't see any level with 2 or 3 atoms up there. After all, you expect a Poisson distribution of loading atoms into the traps, and this Poisson distribution was simply absent. A big surprise. It was quickly understood that what happens is that because the trap volume is so small, as soon as on the order of a wavelength cubed, a little bit more than that, as soon as you have 2 atoms inside the trap, they interact very strongly with resonant dipole-dipole interactions. And so what happens is they form molecules, and at least one of the atoms is ejected from the trap. So what you should imagine here is that for very brief times, maybe a few microseconds, there are actually 2 atoms in the trap, but it's too short to record, and then say 1 or 2 of the atoms are lost. So this made it possible to probabilistically, with about 50% chance, as you see, trap atoms. And I think this experiment was really remarkable and maybe not quite, its significance not quite understood at the time, a little bit more than 20 years ago. So the probability of trapping n atoms simultaneously is exponentially small. So 2 groups, Mark Saffman's here in the US and one in Paris, did experiments with 2 atoms where they loaded probabilistically 2 atoms, but that was about it. It just took too long to trap 3 or 4 atoms simultaneously. But what was around in the field was the idea that you could in principle observe this and apply real-time feedback. So what we did with Misha Luque and Marcus Greiner at Harvard is to, instead of setting up a single trap, we used an acousto-optic deflector of wonderful devices that if you send a radio frequency in, you get a laser beam deflected, and you can send in, say, 50 or 100 tones, and then get 50 or 100 laser beams that you can focus. So you can make 100 traps or so. Now you can load them probabilistically. You can have a camera look at the atoms, and then a computer system decide which traps are filled and which are not. You can discard the empty traps and rearrange simply by changing the frequency of the tones, the other traps, to sort the atoms as you want. And so in first experiment, this was in 2016, less than 10 years ago, we sorted things in 1 dimension. So what you see is here 100 traps. The little bright dots are actual atoms on a camera. The system is a little bit slowed down, and you can see that the computer is able to sort them with maybe an error of 1% or so. Sometimes an atom is missing in the process. But this allowed one to deterministically make atoms in 1D, and then quickly also in 2D. This is from 2020, the sorting in 2 dimensions of a grid in 2 dimensions. You can see we can do almost perfect grids in this case of 225 atoms. On the right-hand side, these are the remaining atoms. And then even in 3D, this is possible. You can guess which country this group comes from. This is Antoine Brouvet's group, a beautiful work of trapping atoms in 3D. We really like 2D because it allows us to have a laser access along the 3rd direction without having to go through layers of atoms, but this may become interesting as quantum memories in the future. Where are we today? I will show you just as a taste a movie where we now sort continuously up to 3,000 atoms in the system. Then we discard some of the atoms, we replace them, etc. Again, this is not a cartoon or a made video. These are actually pictures from the lab of atoms being collected here from a region, from a dipole trap, being sorted and placed. So what do you need for doing actually full quantum computing? Well, you need qubits. In particular, you need many, many qubits to make something interesting, or many means at least 100 or so. You need single qubit gates, the rotations in spin space. These are relatively easy. Basically, this is just laser beams shining in onto the atoms for a certain duration. What is harder to do, and you might think impossible in these systems, are 2 qubit gates. How do I make a spin-dependent or state-dependent interaction between 2 atoms? And then if you have all that, you need low error qubit gate rates, and ultimately we understand pretty well today to make really interesting things, you need to correct quantum errors, so you need logical qubits, you need somehow to redundantly encode the quantum state of the atoms, not in 1 atom, but into many atoms of the qubit, and correct errors for really deep quantum computation. So how do you do single qubit rotations? That's actually relatively easy. What do we use as our qubit? There are several approaches. We use rubidium atoms that have a hyperfine structure, and we choose two of these magnetic sublevels split by a hyperfine splitting that are insensitive to magnetic fields. So for the experts, this is the F equals 1 MF equals 0 state, and this is the F equals 2 MF equals 0 state of a rubidium atom. And then basically we can do rotations between them simply by applying a Raman laser beam, a 2-photon transition between these two levels. Ignore this picture, this is for Rydberg gates. But here are rotations in spin space, and one can make these rotations very good. At the time we had 2 times 10 to the minus 4 errors, and that's much smaller than the residual errors, so kind of the single qubit rotation problem is essentially solved, and we also do that not on one atom, but actually on collections of tens of atoms, up to 100 atoms or even 1,000 atoms. This is the state of the art of the field. Something new we did is, before we were always measuring the state of the atoms by pushing one of the states out and measuring the other. It turns out that in quantum error correction in particular, you can win by actually being able to measure not 2 states by 3 states, namely atom is in one of the spin states, atom is in the other of the spin state, or the atom has been lost from the system. And this loss can happen because we have a finite vacuum. The vacuum lifetime is seconds to minutes. But there are also other processes as we do the gates that lead to a little bit of a loss of atoms. So it's nice, very useful to be able to detect the atoms. So how do we measure the spin state in the newest iteration? We take an optical lattice that depends on one of the spin states, that basically is there for one of the spin states and not for the other. And we have here this optical trap coming from this focused laser beam, this optical tweezer. And now as we move this tweezer across this lattice, one of the states that sees this lattice gets spinned, and the other spin state that doesn't see this lattice gets transported over. Then we can turn on both of the laser beams again, and then we have mapped the spin of the atoms now to a spatial position of the atoms. And then we can measure that directly. And so that allows us to measure, is the atom in one spin state, is the atom in the other spin state, or has the atom actually been lost for the system? And the way it looks like here, this is on a string of atoms, I don't know, 50, 60 atoms or so. Maybe more like 30. And what you see here is this map of what you see here is actually Rabi oscillations between the 2 states now mapped onto space. So here we are not transporting atoms, we are flipping atoms between the 2 spin states, and this is one of the spin states, and this is the other of the spin states, and you see how they nicely rotate and can be measured. You can also now have much, much higher data rate. This is more for the experts, but in quantum physics, especially in atomic physics, where the systems are so clean, basically to control something, you need to be able to measure it, and to be able to measure it, you need high signal to noise in the system. And so here we can do Rabi flopping on a very, very fast time scale to investigate where various errors come from with hundreds of atoms. Now comes the hard part, the 2-qubit gates. How can you make them? How is that even possible? So, we have trapped the atoms separately. The distances between them are on the order of a couple of micrometers or more. How can one make interactions between the atoms? Can we make atoms interact over these distances? This is a remarkable paper that came out at about the same time when Philippe Grangier trapped single atoms in a trap, which proposed what seemed crazy to most of us, certainly to the experimentalists at the time, which said you can make interactions if you take the atom out of the ground state where it's nice and stable and you put it in a highly excited state. Think hydrogen with principal quantum number 100. And then you can use this to make quantum gates. That seems like, these states are going to be unstable. How are you going to control all that? That seemed crazy. So basically, these are states like this. Think of hydrogen-like atoms. Rubidium is like hydrogen, but with a principal quantum number of 100 or so, of 70 or 50. And this is an illustration of the state, how it looks like, for instance, for n equals 35. So what is very important in this system is that the electron is actually very far from the nucleus, on the order of basically 1 micrometer, say, for n equals 60. This is a giant, right? I mean, I can take a COVID virus and place it inside the atom, right? And the electron will just be circling around that. So it's a large distance from the nucleus, which means the electric field of the nucleus is very, very small, which means these states are highly susceptible to electric fields. But it also means that these states are highly susceptible to the electric field created by quantum fluctuations in one atom onto the other atom. So what you get, just like in the ground state, but with 10 to the 11 with n to the power 11th power larger interactions is a van der Waals interaction between atoms in the Rydberg state. The electrical polarizability, of course, has been used by Serge Haroche for his Nobel Prize-winning work, and these states were extensively studied by Dan Kleppner. It's kind of interesting how many things that Dan Kleppner studied, who passed unfortunately away earlier this year, are coming back in physics. He studied cavity QED very on. He did Rydberg atoms very on. You, of course, all know that he started the quest for Bose-Einstein condensation, which became so important in our field, etc. So here the idea is we can now place atoms at a few micrometers from each other, and we can still get megahertz interaction strength over 10 micrometers or so, or even gigahertz or hundreds of megahertz interaction strength over 2 microns. So one way to think about it is to say, if I place the atoms at some distance, which is larger than a characteristic radius, and I try to excite both atoms to the Rydberg state, I can just do that, and both of them will be excited. However, if I place them closer to each other, then if one of the atoms were excited to the Rydberg state, then the Rydberg-Rydberg interaction due to this very floppy electron around the nucleus will now be large and will shift this other atom's state out of resonance. So if I excite one atom, I cannot excite the other atom. Of course, I could have excited the right atom and not the left atoms. So it turns out that when you drive this symmetrically on both atoms, you automatically create a Bell state, a quantum superposition of basically the left atom being excited and the right atom being excited, and you don't know which one it is. And so once you have a Bell state, you can make a quantum gate in the system. This was first done with 2 atoms. The quality in the beginning was not very good, but recently the field has made much progress. I'll show you data from our collaboration, where basically we run parallel gates and we quantify them by repeating the gates in a benchmarking procedure, and we get 99.5% fidelity for now a 2-qubit quantum gate, or 0.5% of error. This is important for 2 reasons. One, it's really the limiting step. Everything else is better than this 2-qubit quantum gate, so this is where the direct improvement can come. What is more important is that there's a so-called threshold for quantum error correction, which is around 1%, maybe even 2%, and so for the first time, the groups are now below that threshold. So we have now are able to start logical qubits. To take advantage of the full strength of the system, I just want to show you something that we can create entangled Bell states, and then simply by moving the laser beams, by moving these radio frequencies going into the acousto-optic deflectors, we can basically start with the atoms close, transport them over hundreds of micrometers, bring them again together and measure the quality of the Bell state. And if we do things right and do some certain decoupling spin echo sequences, we see no deterioration whatsoever of the Bell state unless we transport too fast. And typical time scales are 100 microseconds for 100 micrometer, which is an interesting length scale, or 1 meter per second. So one can transport these atoms and thereby connect even distant atoms to one another directly, rather than having to transfer the quantum information between neighbors, as would be, for instance, necessary in superconducting qubits. Now, quantum error correction is one of the most remarkable, in my view, kind of ideas in maybe not only physics, not only quantum physics, not only physics, but in much of science of the last decades. Namely, you take a quantum system and you can correct errors. Classically, of course, we know how to do it. We just encode things redundantly, right? Say I have a string of, classical bit string of what, 9 bits, and then, maybe 2 of them have errors, and I just look at the system, I say, 2 of them are red, but the majority is white. It's much more likely that 2 have an error than that 7 have an error. It's exponentially more likely, and so basically I can correct the error by looking at the qubits and rotating the red ones back to white. And of course, as I make this string longer, I gain exponentially in my quality of my error correction. But for quantum bits, it's not at all obvious that you can do it, because you, of course, you're not allowed to look at the bits. As soon as you look at the state of the qubits, you destroy the system, right? That's the whole point of quantum states. So how are you going to do that? It's not obvious. Nonetheless, people came up with a multitude of codes, and this is one of the favorite codes. Namely, what you can do, instead of checking what is the state of an atom, you can actually check what is the relative state of several atoms in a structured way, without actually knowing which atom is in which state. So you just compare, if you want, the parity of the atoms. And so in this code, for instance, the white qubits, the white atoms, encode the data. If one of them, say, has an error, in the simplest example, you run parity checks with the green grid of atoms, the dark black atoms, and then basically, for instance, if you had a Z error, these two green atoms that you can measure separately would light up and would tell you that, yes, it is this qubit that had an error. If everything worked perfectly, this would be very easy. The problem with this is that your checking operations themselves have errors, right? So you might draw the wrong conclusion, and if more than one data qubit has an error, it may be hard to disentangle, which combination of data qubits has the actual error. Nonetheless, so maybe basically the thing to take away from the system is if you try error correction, and if your physical gate errors are larger than a certain threshold, then because you need more operations, more physical operations, trying to do logical qubits, you're going to actually do worse. But below a threshold, as you increase below a threshold of the physical gate error, as you increase the size of the qubit code, if you increase the redundancy, then the system should actually start to outperform the physical qubits. And this is the so-called threshold law, and then it scales basically as the size of the system. So here we implemented this year D=5 surface code. So what you see here is atoms. Half of them are data qubits, these are the stationary ones, and half of them, the other ones are the ancilla qubits, the syndrome qubits, the ones that measure errors. And so basically we move these ancilla qubits to the neighborhood of the data qubits. Each one is moved close to 4. And each time when they are close, we perform a quantum gate between them. And so in the end, if the 4 qubits, neighboring qubits, have all the same parity, if they're all in the same state, then the syndrome qubit will be in one state. And if one of them is wrong, the syndrome qubit will be in the other state. And so we can then transport these qubits out in a different region, reach them out, and then in principle correct errors. And we could show that the D=5 surface code started to perform better than by about a factor of 2 than the D=3, the smaller surface code. And this is also about where superconducting qubits, the work of Google, is right now. However, we think we can scale our system very well. So this is how a neutral atom quantum computer will work, one of the near future devices. It will have several regions. It will have a storage region that we can fill to load data on ancilla qubits and to prepare them so that we can use them as atoms are lost from the system. It has an entangling zone where we shine different laser beams to entangle the atoms to do Rydberg quantum gates. It has a readout zone where we read out the state of the atoms, and then it has maybe another reservoir. So basically here we store just atoms in the reservoir, whereas here, the upper region is really a quantum memory. It stores the quantum state as we perform the computation. And for that, to make these systems large, we need to replenish atoms. So here first I'll show you just very quickly a movie where we run a code that is like effectively a 4-dimensional code, but because we can move the atoms in an arbitrary geometry, we can realize an arbitrary dimensionality of the system. And as you see here, there's a complicated code that forms 2 hypercubes that are then read out. And so maybe just this, to finish up this movie where we load atoms, we can now load atoms, reload atoms at 30,000 atoms per second or so. And so we think this will be enough to maintain operation with tens to 100,000 or so physical qubits. And with that, I'm running out of time, and I would just bring up the summary and outlook side. So the takeaway message that entanglement is turning from something that we find strange and that we study and that we are surprised at to actually something we get used to, and it's really becoming a tool. You can use it for quantum sensors, for optical clocks, but you can, of course, also use it for quantum computing. And technologically speaking, the two are very, very similar. In both systems, you want to maintain coherence a long time. You want to maintain entanglement a long time. You need very, very precise lasers, power, frequencies, etc. And this is why what enables this similar, seemingly distinct work to be going on at the same time, often in the same labs. And with that, I thank you very much for your attention.